In this video, we're going to look at friction and equilibrium, and then there'll be a second video to follow on from this. But let's just remind ourselves the friction force F is mu times R, the reaction force. And we'll go through it in a minute, where mu is some coefficient of friction and depends on the surfaces involved. That's a function of the surface over which something's happening. So sandpaper will have a different coefficient of friction to a block of ice. Okay, a 2 kilogram mass rests on a table with mu equals 0.4 and a force P is applied. See, the force P is applied like a rope from the center of mass trying to pull the object along to the right. What is the minimum value of P to cause movement? So what's the maximum value P can have to keep the system in equilibrium? And that'll be the turning point, because to go over that value of P, and the block will start to move. Okay, so it sits at rest on the table there. And what we do is we use the particle model again. We imagine the entire mass of the block is concentrated as geometric center right here. Okay, and all the forces act through that point. We need to choose a coordinate system here because we've got forces going in opposite directions. So we'll choose to the right in the horizontal direction. It's two-dimensional problem, so Cartesian system X and Y coordinates mutually perpendicular to each other. We'll choose to the right as positive and up as positive. We don't have to, we can choose the opposite to that. So long as we're consistent in what we do, it'll all work out correctly. Okay, so this block sitting here has a weight force in m times g. It's mass times g. G will depend on whatever gravitational body this block is sitting on, this surface is on. The surface provides a reaction force, so the weight force pulls down, and with a force of 2 times g. The reaction force is equal and opposite to that, pushes back up, okay, in the vertical direction. And then we have here is our friction force acting to the left. Now, our friction force acts only up to and including a maximum value before the block will start to slide. Okay, so a small amount of P and the block doesn't move because friction can hold it in place. Apply too much force and the block slips and it starts to move. What is the point at which it just begins to slip? What's the maximum value P can be before the block starts to move? Okay, so or in other words, what's the other way? What's the minimum value of P needs to be applied in order to get the block to move? All right, now for equilibrium, all the forces must sum to 0. Can't be any other way. All right, now when we say the block is in equilibrium, what that means is the block will remain at rest because there's no net forces acting. It's in equilibrium, meaning that no net forces are acting, which means that the block is either at rest on the surface here or it's moving with constant velocity. Okay, if its velocity changes, then there's an acceleration. If there's an acceleration, then there's a net force. So that can't be possible. Here, the net force is 0. It's equilibrium. Okay, so let's start in the I direction. We're going to have a P cos 60 degrees here in the I direction. Did I go too far with that one? I think I did. All right, let's start again with that one. Draw it a little bit more proportional. So I'm going to have a force here this way. Okay, that'll be the cos of this. So it'll be P cos 60 degrees. P cos 60 degrees minus a friction force, because the friction force is to the left, it's in the negative direction. P cos 60 degrees is in the positive direction, so that minus F is 0, because with equilibrium, the force in each of the different mutually perpendicular directions must sum to 0. In the J direction, we have plus R going up. Well, that's in the positive direction, so we'll write plus R here. We have a sine component here. Okay, that's P sine 60 degrees. Now again, that's in the upward direction, so that's plus. And then balancing all that is the weight force, 2g down. So minus 2g, minus because it's in the downwards direction. All that's equal to 0 as well. Okay, good. Now, from equation 1, we can write F is P cos 60 degrees, and that's equal to mu times R. Okay, and so we can write that as Okay, P cos 60 degrees is equal to mu times R, and we got R, the reaction force, is P cos 60 degrees on mu, okay, which is 5 on 2, because remember the coefficient of friction was 2/5, okay, so that is mu was 2/5. Remember we had that up here, mu is 0.4, okay, which gave us 2/5, okay, and the reciprocal of that is 5 on 2 times cos 60 times P. Okay, so far so good. Okay, so you put 5 on 2 P cos 60 degrees plus P sine 60 degrees. Where did that come from? Okay, well here's the second equation. We're putting R in, which is 5 on 2 cos 60 degrees P, so that goes there. Plus here P sine 60 degrees. Okay, that's good. Minus 2G is 0. All right, well, next step then. Let's take the minus 2G onto the other side over here. Let's write cos 60 degrees times 5 on 2 gives us 5 on 4 because cos 60 degrees is a half, so we get 5 on 4. Sine 60 degrees gives us root 3 on 2 times P, and that's equal to 2G. Okay, let's multiply through by 4. So what we get here is 5P plus 2 root 3P plus 8G. Factor out the P. So we get P times, in parentheses, 5 plus 2 root 3 equals 8G. And so P is 8G on 5 plus 2 root 3. Now using G as 9.8 meters per second, putting that through the calculator, we'll have P is approximately 9.62 newtons. All right, and that's it.